All right, let's begin. Let's have a look. So, power functions. We're referring to exercise 7a, but area study, 12.1, graphs. There's a whole bunch of functions that you have to understand the features and its properties and be able to identify them. So the first one was functions x to the power of n. Now, n can be a rational number, it could be an integer. It could be negatives, it could be positive, it could be whole numbers, whatnot. That's what the Q stands for. The Q is rational numbers. And so therefore, we're looking at all power functions where it's x to the power of, let's say, 1 and 2, 1 and 3, 3 and 5, negative 3 and 5. You need to understand what the properties are and where or what it may look like. Okay, so today's session, I'm going to explore, just revise the first three, but then there's one that I thought we didn't really cover well, or we didn't really talk much about it, which I'll mention and get you to think, because it's not about memorizing these functions, but it's about identifying the key features of what you already know from year 11. Okay, so let's have a look. Yes. Okay, so you got even, odd power functions, and these are your three that we would have talked about in chapter 1. You have, if you got an even positive, odd positive, so meaning just a whole number that's even or a whole number that's odd. So x to the power 4, for example, x to the power 3, yeah, even, odd. Or you have even that's negative, so negative 2, or you have negative 3, right? And then you got your even functions where it's a rational number, so 1 on 2, 1 on 4, 1 on 6, versus, let's say, 1 on 3, 1 and 5, 1 and 7, 1 and 9. Okay? So these are the ones we would have done in chapter 1, and I would have tried to explain each one. And I want you to see that these are the shapes that you're familiar with, in such that the first one, x to the power 4, is technically the same as your quadratic, or x to the power 6, or x to the power 8, or x to the power 10. It carries the same property or shape, in the sense that it's symmetrical for even numbers, because it makes sense. Every time you square a number, all the negative values become positive. And, you know, let's say x to the power of negative 2 to the power of 2, or negative 2 squared, is the same thing as 2 squared. So that's why it's symmetrical. It looks exactly the same. So that means x to the power 6 is going to be the same thing, because it's the same thing as saying x squared to the power of 3. This is x squared to the power of 4. This is x squared to the power of 5. That's why it is possible to generalize this to all positive values, which I'm going to write here again, just so you remember. This is the same thing as writing x squared to the power of 4. This is the same thing as saying x squared to the power of 5, because you multiply the powers together, it gives you x10, right? Same thing with x to the power of 5, x to the power of 7, x to the power of 9, x to the power of 11. It follows the same shape. And then you look at even negatives. You got your truncus function, even negatives, so negative 2 gives you a truncus function. And again, it's the same thing. Of course, 1 over anything, 1 over an x squared, because technically I'm just rewriting it over here. You know that x can never be 0. X cannot equal to 0. X squared cannot equal to 0. And so therefore you have asymptotes. So that's why any rational number, as soon as you have 1 over x to the power of something, you know there's an asymptote. And that's one of the properties that you have to identify. Okay, so it could be 1 over negative 3, same thing. 1 over x to the power of 3 still has the same thing. It has an asymptote, which you can see in both cases. Now the difference between the two, well, again, squaring. See, every time you've got a negative x value, every time you square it, it's exactly the same thing as if it was positive. It's very similar to your quadratic. Same property as the cubic. You can have negative values. That's why you have negative y values. Okay, so you can think of it as negative 2 to the power of 3 versus 2 to the power of 3. One's 8 and the other one's negative 8. That's why you can see the differences between the two. Okay, so that's your even, odd, and you would have seen that in year 11. So you've got quadratics, cubics, truncus, rectangular, hyperbola. Yeah? And then you go to year 11 again over here, which is touching now year 12. You learned square root functions, x to the power of half. Square root functions, that means x to the power of a quarter, x to the power of 1/6, x to the power of 1/8 is the same thing. Because another way of thinking about this is the same thing as saying square root function, and you square root it again. So of course, you can never have negative values. Every time you square root a negative value, it doesn't exist. That's why there's never a negative value. And so even if you double square root it, it still doesn't have a negative value. So x to the power a quarter, x to the power 6, x to the power 1, 8 will follow the shape. The only difference is whether the x values are getting larger or smaller. Okay, and that affects your y values. And then if you pay attention to x to the power 1/3, well, the difference is it can have negative values. You can cube root -8. You can't square root a negative, but you can cube root a negative. You can think of -2 times -2 times -2 can give you a negative value. That's why you can cube root. And so that makes sense why you have a negative value. But notice, these two values would be exactly the same if this was -8 and this was 8. Cube root of 8 is 2, so it's +2. And then cube root of -8 is -2, so it's the same distance. The only difference is it's different in terms of its powers. Oh, sorry, it's in values, y values. Okay, so in terms of its direction, but in terms of its magnitude, it's the same thing. Okay, so these are the two things, and the one thing I wanted you to take out of these two is that all even functions generally have a symmetrical property because you're squaring it. Those are the key things. As soon as you see a squared, you start thinking that negatives will become positives. Okay, and then whereas odd functions are usually asymmetrical, in the sense that if you have positives, you'll have the negative sides, but it's the same values but different direction. Now these are the ones that we would have covered in chapter 1, and I would have played around on Geogebra to show you, what if I increase 1 and 5, 1 and 7, how does that affect the graph? And we can do that logically. We can think about, as the denominator increases, then y values get smaller, because 1 divided by a very, very large number becomes a very, very small number, which is why you have that asymptote coming along. Okay? But the one that I want to talk about today, power functions, the one that I think we haven't really talked about. We talked about even, odd, whole numbers that are positive, negative. Yeah, that's the first two boxes. And then you talked about rational numbers where it's 1 and 2, you got odd and even. But what haven't we talked about is negative. We haven't talked about, what if I asked you x to the power of -12? What does that look like? If I asked you to sketch me or roughly predict what x to the power of -1/3 will look like, how do you know? What does it look like? You can actually do this if I actually write out the function for you. X to the power of -12 is the same thing as saying 1 on x to the power of half, which is the same thing as saying 1 root of x. Now you can use your understanding about properties of what you already, or what you already learnt, and you can actually tell me what it may look like. You got 1 over, and I told you if it's a fraction, you cannot have the denominator equal to 0. Square root of x can't equal to 0. You have an asymptote. So already you know we've got an asymptote at y equals 0. You know that as you increase, if x increases, y gets smaller because 1 divided by a very large number becomes a very small number. It's like 1 divided by 10, 1 divided by 100, 1 divided by 1,000. You notice it goes from 0.1 to 0.001, and it gets smaller and smaller. So it makes sense that if you increase the denominator, y values get smaller. So the only other thing that you have to pay attention to is square root of x. The restriction on square root, we already know you can't take negative values. So that means this graph looks like your normal rectangular hyperbole where you have an asymptote, and as you increase it does go like that, but the difference is it doesn't have negative values. So that's it. That's your graph. The values might be different, like in terms of where it goes, but the shape, you can already predict what the shape will look like. Okay, so you don't have to memorize these, or if you want to, then you can memorize these shapes and write in your cheat sheet somewhere. But this is it. I'm going to show you over here just to analyze the shapes here. X to the power of -12, that's your shape for x to the power of -12, and that's what I'm saying. If you look, there's an asymptote along this line, which makes sense. And there's an asymptote at the y x equals 0. Same thing as your rectangular hyperbole, the values might be different, but the concepts are the same. This is still very similar to 1 on x. The only difference is you said square root x, because x to the power of half is square root. So this is the same thing as 1 on x to the power of half, which is the same thing as saying that. And so it makes sense that you can't have any negative values and you only get the shape. Okay? Now that also then means that you can also apply that to x to the power of negative a quarter, x to the power of negative 1/6, x to the power of negative 1/8. It will follow the same thing. The only difference is whether it's larger or smaller in terms of y values. Now then the next question is then, okay, so that's even. It makes sense that every time you have 1 over x root of 4, you know you can't have negative values, so that makes sense. Well then, what about odd? What if you had 1 over x to the power of 1/3? Let's think about that. If I gave you that, if it was x to the power of negative a third, right, which is the same thing as 1 over x 1/3. Again, it's a fraction. So what do you know? What's one property that you definitely know? It's 1 over x to the power of any. I don't care what the power is, but 1 over x will imply what? What property should you be taking out of this? Yeah, you should have an asymptote. So you already know there's a y equals 0 asymptote. You know that x to the power of a third cannot equal to 0. And so you got x equals 0 and you got your y equals 0 asymptote already. Now let's think about it. If I increase x, I don't care what the power is, just think about the x value. If x became really large, if I said this is infinity to the power of third, regardless, it'd still be 1 over infinity to a third. Just logically think, 1 divided by a very large number, what does that become? Is it getting smaller or is it getting larger? Smaller. So the property sounds like it's very similar to your rectangular hyperbola again. Now the only difference is, can I have negatives? Yes, I can. I can cube root negatives. So if you think about this, this actually now looks very similar to your rectangular hyperbola because logically, yes, it still goes in the same direction. Now what's the difference? And this is what I want you to pay attention to. What is the difference for x to the power of negative a third versus this one? Because I said it was very similar to x to the power of 1 on x, which is rectangular hyperbole, or x to the power of 1 on x cubed. They both have similar shapes. If you look at this shape and this shape, don't they look very similar? But can you spot out the difference? What's the one difference? I want you to pay attention. What's the one difference there? What's the difference? There's one key difference that makes x to the power of negative 1/3 and then x to the power of negative 3 different. It's a key point here. And logically, you can even figure it out as well. No, the asymptotes are the same. It's just that I've zoomed in. If I zoomed out, this would actually eventually go to 0 as well. Okay, so I want you to look at this graph and this graph. Yeah. So the difference between these two that I want you to pay attention to is that this takes a while to reach the y-axis, or another way of thinking about it is the x values get closer to 0 much faster when it's 1 on x cubed, versus this one takes longer to reach y equals 0. This one is quicker. And if you think about it logically, it makes sense because 1 over x to the power of a third versus 1 over x to the power of 3, well, yeah, logically it makes sense because if I put a super large number in here, well, if you're cubing it, of course it's super, super large. It's being cubed. So 1 divided by it, of course it gets smaller much quicker. Whereas what is this saying? If I put 1,000 in, then you're cube rooting 1,000, that makes it 10 now. But if I put 1,000 in here, this is now 1,000 to the power of 3. Of course that's going to get super small very quickly. Whereas this one takes a longer time. So that's why graphically, yes, it does. The difference is that it will take longer to get smaller. But on the flip side, that means when this is a fraction, it gets super quick, it reaches infinity much quicker. So it reaches y equals to infinity much quicker at a fraction, whereas this one will take longer. That's the difference. It's a subtle difference, but it's key in terms of analyzing those points there. That's why I don't want you to memorize that. I want you to analyze it. What if I put a very large number? What if I put a negative? How does that affect? I'm just talking about even and odds. Yeah? So, the one thing I want you to take down is in terms of your notes, even negative rational numbers, which is what I was saying at the start, even rational numbers, which is this one, whoops, which is this, are similar to your even negative graphs. They both share asymptotes at y equals 0, x equals 0, as x increases, y increases. That makes sense. And between 0 and 1, y increases. That's very similar for both cases, okay? For even negative and even negative rationals. But then, the difference is even negative rational powers cannot take x values. That's what I was saying. 1 over square root of x, or 1 over x to the power of fourth root of x, we know that it can't take negative numbers. That's the only difference. Whereas your odd negative rational, that's what I spent a bit of time trying to describe to you, that as you increase x values, it takes longer for x to the power of a third as an odd rational number to reach y equals 0. Yes, Kareem?
I don't understand the even negative rational ones. Why you say that between 0 and 1, why it increases?
Because it becomes a fraction. So what happens between x equals 0 and 1? Now, so between x equals 0 and 1, which is here, y values are starting to increase. Sorry. Oh, okay, I get what you mean. Okay, I think what I'm saying is as x approaches 0, as it gets smaller, so between 0 and 1, as x is approaching 0 and it gets smaller and smaller, then y values are getting larger and larger. That's what I meant. Sorry, thank you. Yes, that is true. What I'm saying is if you put a limit and you say as x approaches 0, as it gets smaller and smaller, y values are getting larger and larger. That's what I meant. Okay, I'm going to write it here. As limit of x approaches 0 or gets smaller, y values get larger. Okay. Now I'm going to show you that. I'm going to show you this onto Geogebra so you can see what happens if I now ask you x to the power of negative 2 on 5. What does that look like? What if I asked you x to the power of negative 3 on 5? What does that look like? Because every one of that, I want you to have an instinct of what it may look like. Because to the power of 1 on 5, you already have this thought in mind. It has to look very similar to your rectangular hyperbola. And if I said 3, it's just cubing it. So you're just making it larger. If I said squaring it, then obviously now it looks more similar to a truncus. I'm going to show you in Geogebra, and I want you to download it and play around, really play around the negatives, positives, numbers so that you can really understand. Okay? So let's have a look at Geogebra. Now, when you're using Geogebra, just keep a note here if you want to play around with my sliders. These are called sliders. You got your A, B, C, D. A, B will control the first 3 functions. So you got 1, 2, and 3. Okay, that will play with the first 3. And if you want to control the last one, that's C and D. The reason why I've got 4 functions there so you can compare. And what I mean by compare is one of it, for example, I can do, let's say I want to compare fractional powers. Okay, so if I pull this out, and I pull this out, I'll just make this larger so you can see. I want you to see that if you wanted to compare what happens when you increase the values, okay, what I want you to see is this is currently x to the power of 1 and 2, and this is x to the power of 1 and 1. So if you wanted to compare it, you can play around. Let's say you make D2, so that's exactly the same graph. And the question is, if I change my B term, my A term, what happens if I increase it to 2, 3, 4? It's all out of 2. It's still 5 out of 2. So if you look at the graph, it's still 5 out of 2. You can do a comparison. That's why I've got 4 functions, so you can do comparisons there. What I want you to see as well, in terms of my questioning in the PowerPoint, for all rational powers, I want you to think P on M. I want you to think about 2 things, or notice 2 things when you're playing around with this. And the next part, it tells you what I'm trying to explain. But I want you to notice 2 things. 1, what happens when x to the power of negative 1 and 3 versus x to the power of 3? What happens between them? What's the difference between them, which we described already in the previous slide? I want you to play around with that. And then what happens when rational powers have a larger numerator than its denominator? So the example I gave just now was, what happens when you have 5 on 2? That's larger. Numerator is larger than denominator. What happens? What if I change the denominator to 5, for example? Okay, and then I said it was 3 on 5. Okay, In comparison, let's say I'll do 5 again, and it was 1 on 5. So this is, you can see the color purple, 1 on 5 looks like this. So what happens when I increase it to 3 on 5? See, 3 on 5, if you think about it logically, it just means that every one of these y values is being cubed. Because another way of writing 1 on 5, x to the power of 1 on 5, sorry, 3 on 5, is the same thing as writing x to the power of 1 on 5 cubed. So all you're saying is take the y values and cube it. So it makes sense. Why? It looks like the green shape. So at 0, 0 cubed, of course it's 0. But as soon as you take all the positive values and you cube it, of course it's getting larger. It makes sense. Whereas the fractional values, if you cube it, of course it gets smaller. Okay, so what I want you to see is, okay, it still maintains the same shape where it kind of looks like an S. At what point does it not look like an S anymore? So I want you to think about it, and this is what I was mentioning in chapter 1. If you watch, as I increase A to 4, even powers. You see, if it was 2, it still carries the same shape if I made it 2. So this is 2, carries the same shape. Why? See, if you think about it, this is the original 1/5, x to the power 1/5. If you put 2, that's the same thing as saying take that graph and square it. So it makes sense that all these values here, that's negative y values, they get squared. So of course it goes up. Everything gets squared, everything becomes positive. That means all these values are also getting squared. That's why it has that green shape. So that means x to the power 4 is the same thing, except you're squaring that as well. So now, if I increase that to 4, of course it gets larger with the same shape. Now I want you to see, as soon as I hit 5, because it's to the base 5, if I hit 5 on 5, makes sense, it's a linear. Yeah, x to the power 1. So what happens if it's 6 on 5 now? And this is what I wanted you to pay attention to. If the numerator is larger than the denominator, let's have a look. If I increase it to 6 on 5, what would you predict it to look like? And this is what I'm saying in chapter 1, I said that it would now tend towards, it's a dilation towards your y-axis. Whereas right now it's dilation towards your x-axis. So if I increase this to now 7, you can see now it's heading towards the other direction. So compare 7 and 3. So this is 3. See how it's heading towards the x-axis. It's getting stretched along this line. But as soon as I make it 7, 9, or 11, you'll see that it'll head towards the y-axis. So if I increase it to 7 now, this is 7. And then if I increase it to 9, you see how it's curving the other way. It's now more like your cubic graph. Which makes sense, because if you wanted to make it a cubic graph, if instead of 9, if you had 15, 15 divided by 5 makes it 3. That's why you get your cubic graph. That's why it looks like that. Yeah, 15 on 5 is 3. So that's why it looks like that. Whereas if it's less than 5, then of course it looks the other way. Okay? And that's what I want you to pay attention to. As you increase the numerator and denominator, what's happening. And if you start paying attention to that, you don't need to memorize what the graphs look like, because there's infinite power functions. And it's not that in your exams that they will do that, but I just want you to start analyzing graphs. That's the skill that you need to take out. Okay? And so that's what I want you to do with this Geogebra app. If you want to compare, use 2 of them. So these 2 dots over here, you can hide them away and reopen it. If you drag it across and then right click, you can change the equation so you can compare them. Okay, so and remember, AB controls the first 3 functions and C and D controls the last one. Now I already wrote that in the PowerPoint in case you missed out. Okay, so it's on the top right corner for you to read. And in case you weren't listening to what I was saying today, I already answered the question of what I was saying. Okay, so when you increase your denominator or numerator, what happens, what it looks like. Okay, now that you understand what I'm saying, hopefully, let's have a look at this then. F of x, if we were to sketch x to the power 2 and 3, I want you to, either on your surface, on your paper, on whatever you have right now, roughly draw it. What do you think 2 to the power 3 will look like? Now I already broke it up for you. I wrote x to the power 3 squared. So you think about a third. Can I have negative numbers? Do I have asymptotes? What happens if x is infinite? It was large. Okay, think about, what if it was a fraction? Will I have increased y values, decreased y values? Predict what this graph will look like, and then I'll show you. Okay, and then same thing with 3 on 2. If we switch the 2 powers, notice 3 is the numerator and it's larger than 2. So which direction should it be heading? If you can predict that, that means I can give you any other graph that's a power function, and you should be able to do, whether it's negative or positive. Okay? And then I want you then to work on this VCA question to work back on the functions, inverse functions, composite. That's what chapter 7 is about. It's revisiting chapter 1. Okay, revisiting chapter 1. So thinking about it, x to the power of 1/3 is cube root. As a cube root graph. Just in case you still couldn't get just a cubic graph, this is your notes from the first slide. That's what a cube root graph would look like on the right hand side here. So all you have to understand now is if I have 2/3, which is the same thing as saying squaring the cube root graph, what happens when I square that graph? What should it look like logically? Okay, if I had to square all of the y values right now, everything you see there, I'm going to square, what would logically happen? Okay, so I'm just saying this is your graph, and I'm going to square it. Square every value. Hands up. If you were predicting a graph that looks similar to something like this. Good, excellent. Because all I'm saying here is I'm just squaring, so it becomes symmetrical. Remember, 2 is an even number. That means all these values are getting squared, so of course it gets larger. All the negative y values, though, because it's getting squared, it's going to be positive. Now it's symmetrical because cube root, remember, cube root of 8 and cube root of -8 is the same value. It's just a difference in distance. So if it's -2 squared is the same thing as 2 squared. So of course it's symmetrical. So your graph should look like this. There you go. It looks exactly the same except it's steeper. And that's your graph of 2 on 3. Now, if you had a look at 3 on 2, same thing again. If we had a graph of look at 3 on 2, it's the same thing as saying your square root graph and you're cubing it. Because 3/2. It's the same thing as saying 3 times the 1, which is 3 and 2. This is your square root graph. If I'm cubing it, obviously it's just getting larger, right? But you still can't have your negative values. You can't have your negative values in there. So therefore, it should just look like this. Now, hands up if you actually curved it towards your y-axis. Because remember I said if the numerator is larger than your denominator, it will now start heading towards your y-axis. Because right at x equals 2 on 2, it's the same thing as a linear graph. So if you dilate that, of course, it's now curving towards your y-axis, whereas your square root function would have looked like this. So if you did this, it's wrong. Okay, you had to write it, draw it such that it's heading in that direction. Okay, so this is wrong, this is right. Okay, that's all I wanted to teach today. So what I was trying to teach you is GeoGebra. Pay attention to the numbers, the fractions. It's the rational ones that I'm more concerned about. And what happens when it's negative. Pay attention to the properties. If you have an asymptote, and you start questioning in that way. Every function you get from here, whether it's composite, sums, products, differences, start analyzing it the way I'm telling you to. Ask the questions that I'm asking you. Okay? So that's it for the PowerPoint for the session. I'm pretty sure there's no... Yeah, that's it. Okay, cool. I'm going to write the solutions for this over the weekend, so I'm going to do a video on it. There are answers on the back. But it doesn't have the actual solutions to it, so I'll do it on a video. I'll post it to you guys. And same thing with your circular functions. Okay? So let's work on this sheet for now. I'm just going to stop the video.